Hello and welcome to our semester project presentation. My name is Ryan Winterhalter and I'm presenting here today with Jake Yocum and Thomas Rafeld, and we will be presenting our final report of the four-way traffic light intersection semester project. In the presentation today, we will start by talking about our abstract and then move into the project objectives before we talk a little bit about some introduction and background knowledge. Then we will move into the methodology of our design, talking about both the hardware and software components of the design. We will then talk about the results and the discussion surrounding our findings from the project. We will talk about the timeline and the budget of the project before we finish up with the conclusion and the lessons that we learned from working on this project.
All right, so the purpose of our project was to eliminate any inconveniences or frustration of drivers and pedestrians at a traffic intersection. The parts that we used were the PIC microcontroller, LEDs, buttons, and 7-segment displays. We used the microcontroller to analyze data from the sensors, and then it would make a decision on the intersection path state. Our project tried to balance safety of the pedestrians and drivers while also making traffic flow efficient. Our prototype was designed as a small-scale model, but it could be scaled up for real-world traffic intersection applications, and our final price was about $46.
So we had 5 main project objectives to try to incorporate into the project. The first one was to develop a loop system in C so that each program of the intersection is able to receive an unbiased amount of time with the green light and program the ability to set a different traffic light LEDs within the code. The next objective after that was to use the vehicle detection sensor to determine the presence and quantity of vehicles at each path into the intersection, and then relay that information to the microcontroller so that it can efficiently govern the system. After that, we then were able to utilize the data from the vehicle detection peripheral sensor and apply it to the path deciding algorithm that was able to perform a delay and a skip into the loop to efficiently determine the set of next appropriate states into the intersection. The fourth objective was to incorporate a push button onto the corners of the intersection to allow pedestrians to input their own delay or skip into the loop, and when they want to change the current state of the intersection to be able to cross the street. The last objective that we did was to integrate a 7-segment display to display the amount of time that the pedestrians were able to visually see to cross the street of the intersection before the state of the intersection will change, or they could see it as to block the ability to cross.
A little bit of background information, introductory information about the project and why we decided to pursue it. Traffic lights are critical to maintaining order at different intersections for ensuring the safety of both drivers and pedestrians passing through those intersections, and they need to be able to operate day and night without any human oversight. So, by incorporating a microcontroller and various sensors into the intersection, we can monitor its traffic flow and be able to determine the appropriate state of that intersection, reading information from the system's different peripheral sensors and changing the different traffic lights as needed. Adding additional sensors into the system will inherently make it more complex, but it adds the necessary functionalities and efficiencies to properly maintain order in modern traffic intersections.
All right, so a bit of background. Current traffic systems rely only on preset program values rather than dynamically monitored values for determining when the intersection should change state. So building a traffic light that has dynamic allocation would ensure smooth and optimized traffic flow and is becoming increasingly important as traffic patterns remain ever-changing. So readings from the traffic intersection sensors can be compared using a predetermined precedence scale, allowing the system to apply a state determining algorithm and decide how long each path should be greenlit based on the current traffic flow. Intersections need to balance all different types of factors, including the presence of and quantity of vehicles entering different parts of the intersection, pedestrians attempting to cross, and previous greenlit path time, as well as other factors. Sensors used in this type of traffic light system application can include one or any combination of radars, camera sensors, infrared motion sensors, pressure or weight sensors, and more, all of which can help determine both the presence and quantity of vehicles at each entry point.
So for the hardware side of the methodology, a total of 12 LEDs were used for the traffic lights. 3 LEDs from 2 of the parallel branches were connected in parallel, allowing for only 6 data pins needed for the MCU. 4 buttons were used on each of the corners, but they were also all connected in parallel, so only one button was needed to be pressed to be able to change the path of the intersection. 8 vehicle detection pressure pads were used, which were buttons as well, and 2 of them were in each entry point to the intersection. These were used to determine which intersection path had precedence by knowing how many cars were in each of the paths. 2 7-segment displays were also used, one for each corresponding path through the intersection as either a walking timer or a stop timer. These are to indicate time pedestrians had to also cross. And a relay allows only one 7-segment to show the path at a time, consolidating 8 MCU pins for both 7-segment displays. This is the block diagram showing that the upper left, upper right, bottom left, and bottom right were 3 each LEDs showing red, amber, and green. There were 2 priority sensors, which were the push buttons, 1 push button in each corner for the pedestrians, and then 2 7-segment displays were also there.
So moving into the code development for the microcontroller, the first thing we had to do was to develop a main loop function that would act as an infinite loop and constantly cycle between the different traffic lights on specific delays. And this delay time between the cycles was determined by either the press of the pressure pads for the vehicle recognition and or the pedestrian buttons on each of the corners. In our prototype, we showed precedence of the pedestrians over the vehicles by implementing an interrupt functionality that could be triggered at any point. When any of the pedestrian buttons was pressed, this would act as a skip and interrupt that would eventually revert back to the main loop function after giving proper time for that pedestrian to cross. Counters were used within the program to record the amount of cars at each path in the intersection and were compared together so that we knew when one counter was higher than the other, the precedence would go to that particular path. And based on a comparison to the current state of the intersection, would change the traffic lights if needed to maximize the efficiency of the traffic flow through the intersection. The extra data bit on port C would output a high or low, which was used to turn the relay on or off depending on which 7-segment we wanted to display for its corresponding path to the intersection. A low signal would connect the I/O pins on the relay to VCC and the 7-segment for one of the paths, and a high signal would connect the I/O pins of the relay to VCC and the 7-segment for the other perpendicular path through the intersection. These are the 2 flowcharts that we used when constructing our C program. The one on the left is the loop function incorporating delays that would actually change the state of the intersection, changing each of the LED lights as necessary. And the flowchart on the right was the state determining algorithm that would read information from the vehicle recognition sensors and from the pedestrian push buttons to determine if there was a 7-segment countdown needed and if there was a state change needed for the intersection.
So some results, we had several setbacks and hurdles that we had to work around, primarily regarding the limited number of data registers in the MCU and the low processing power that it had. We were able to stick with our budgeted allotment of 1 register per category. The new design that we created cost about half as much as our originally proposed budget because we cut the cameras out of the design. The board did offer some lag and missed triggers, which we presumed to be the low processing power of the board. All 5 of our project objectives were met, and the prototype was able to properly model a simplified representation of a real intersection.
So this is the project timeline that we used. This was the original conceived Gantt chart, and our team was able to follow this timeline relatively on T. There were a few straggling derives that occurred across the way, but for the most part, we were able to follow this relatively well.
This is the final project budget. The table on the left shows all of the different components that we used cutting out the cameras and how that greatly reduced the total cost of the budget to about 50% of what we had originally proposed it would be.
In conclusion, efficient traffic flow is becoming a need with increasing population and community development. Our prototype solved many of the efficiency issues in everyday normal traffic lights, reducing the driver frustrations and optimizing travel times. Our team created a smart intersection that was able to survey its surroundings and then efficiently determine how to let the traffic and pedestrians through the intersection without sacrificing safety of either of the vehicles or the pedestrians. The components that we used included the microcontroller, LEDs, push buttons, vehicle detection, and 7-segment displays to determine an appropriate intersection state. We successfully demonstrated the operation of the prototype in which the microcontroller interpreted the information from system sensors and then set the necessary state, revealing the accomplishment of all 5 of our project objectives.
Lessons learned, we learned how to work through all the different stages of the engineering design process. We're also able to learn the development of microcontroller systems and the applicability to solving many different types of problems that are in the real world. We're also able to work effectively and to collaborate as a team to accomplish the shared project objectives and develop a strong prototype design. We're learning more about traffic intersections and the electronics that are involved along with them. In the future, to make this project better, we would include a better algorithm that would be able to minimize the assumptions category that we had to create. And we would also improve the vehicle detection mechanism from a pressure pad push button into some kind of camera and a serial communication.
These are our references, and thank you for watching our presentation.